Good morning. Welcome back to EELE 461-561. This is Brock. This lecture is associated with our Friday meeting time, which would have been held on April 17th. Okay, so let's go ahead and get cranking. So what I want to do is I want to look one more time at this notion of TDR or time domain reflectrometry, because this is really powerful. Last time we looked at, we've been kind of studying this whole coupled lines and the way that, the neighbor will influence the impedance that we see on the line that we care about, whether or not it's the neighbor's at zero, or whether it's being driven in the same polarity, which is even mode, or its opposite polarity, which is the odd mode. And we kind of got to a point where we're like, I want to see this in action. And so we built last time we built an ADS model that had a coupled line, and we wanted to see the impedance of the line that we care about, or an impedance discontinuity, and we wanted to have it change depending on what the neighbor was doing. But it was the first time that we were actually trying to measure impedance in ADS, and we kind of looked roughly at this architecture of a circuit that could do this for us, and it's called a time domain reflectrometer. And it's such a powerful tool. I want to spend this lecture looking at it, and this is almost everything we talked about last time, but let's just review what it is, okay? So the whole idea is that if you want to know the impedance of something, one of the easiest ways to do it is to launch a wave into it and look at what is reflected. And as long as you know the impedance that you are in, then you can calculate the reflection coefficient. Well, you don't even need to calculate the reflection coefficient. You know what's reflected, so you know the percentage, and then if you know what impedance you're in, you can calculate the impedance of the load. And so it's simple, ZL plus Z naught over ZL, or ZL minus ZL naught over ZL plus Z naught. Well, the way that a TDR is built is it's essentially an oscilloscope, and it has built into it a pulse, okay? So you can make a step. And what you do is, it launches a step, but it is absolutely perfect 50 ohms. Like, it is expensive. Okay, they spent a lot of money to make this thing like an ideal 50 ohms. And then you launch the wave out of the 50 ohm system, and anything that's reflected is measured by the oscilloscope, and then you can actually just calculate what is there. And what's cool about it being a 50 ohm system is that you can connect 50 ohm cables to it. So if you put a 50 ohm cable on this that was like 3 feet long, you're not going to get any reflections out of it. It's only when you attach what we call the device under test that you can actually start seeing reflections. And so that's what's really cool about it is, and then this is used to measure, reflections or impedances on other cables, maybe a cable you're building and you want to try to make it 50 ohms. You want to see how bad you're doing. Sometimes it's used for faults. So if you have a cable that's maybe 12 feet long and somebody crimped it and you're like, where did they screw my cable up? You can launch a pulse down it, and you can look at how long it took for the reflection to get back from like a short that might have occurred due to the crimp. And you can isolate where it is. And, printed circuit board traces, you can figure out how well the manufacturer did on making a 50 ohm trace, or how bad you did at calculating the line width, or just flat out components. So sometimes you might have a receiver that's supposed to have a 50 ohm termination resistor. Like on an FPGA, you can program in termination resistors. Well, you turn it on, you blast something into it and see if it reflects. Well, what if you accidentally had it set to be a 70 ohm resistor instead of a 50? So just a million different things you can do with this. Actually, there's one thing you can do with this: measure impedance. But you can measure impedance on a million different things. Okay, remind ourselves how this works. First and foremost, you have a very quick step, guys, because you want to stimulate all the energy you can. So TDR oscilloscopes, they put out like 20 or 30 picosecond rise times. They're blazing fast. That's like translates into 20 gigahertz of bandwidth. Perfect 50 ohms. For what we do with calculations, if we're doing simulations, is we generally put a 2-volt source here, divides over a 50 into a 50 ohm cable, and then you get 1 volt that launches down. In reality, a TDR scope doesn't use 1 volt. It uses whatever it wants to, because if it knows what it started with, then it knows basically what you get back as a percentage of that. So it can divide out divide out what it started with in order to not really care. And that way you don't have to have this thing be exactly 1 volt. It's just if it's 272 ohms or 272 millivolts, that's fine. Just divide the value that comes back by 272 and it's all calibrated out. And so everything is just proportional. I put the 50 ohm here because it's usually a cable. So you usually connect a cable to the oscilloscope or the TDR scope, and then you connect your DUT over here. But this is important because even if you don't have a cable on here, the source impedance of the TDR isn't exactly at the connector of the scope. It resides back a little bit. So even if you don't have this cable connected, there is a little bit of transmission line. Maybe it's like 100, 200 picoseconds, a couple inches between where the source impedance was and the actual connector. So you always have some sort of transmission line that sits after the 50 ohm output impedance. And that's why you put it here. Then if you added like a cable that was a nanosecond, you just change the delay of this transmission line. Once you get to the DUT, the theory of it is that it's probably something different than 50, and you're going to get a reflection. And so then the reflection will happen. It'll travel back here. We observe right here at the TDR node, or we could call it VA, but we basically just look at it with an oscilloscope. And if you remember the math, the reflected voltage is going to be the reflection coefficient times the incident voltage. For our math, we'll do incident goes to 1, and this is a percentage of what was reflected. And it is ZL minus Z naught over ZL plus Z naught. Look at that. That's wrong right there. Check this. Boom, just fixed it. So ZL minus Z naught over ZL plus Z naught. And that's cool because if I can measure the reference voltage and my incident voltage was either 1 volt or it was known, what we can do is just rearrange this equation and solve for ZL. And this is very simple. Basically, if you just rearrange and do all the algebra like we did last time, you plug in Z naught, which we know is 50, and you do 1 plus V ref, or reflected, 1 minus V reflected, and you calculate ZL. Boom, life is good. So let's take an example. Let's do this one, and let's pretend we don't know the impedance of this one, even though you can see what it is right there. Maybe I'll try to cover it with the mouse. Actually, that's stupid. Just don't look. I know you just looked. Okay, so here's what I get. Here's my system. I launch a wave. It comes down here, and I get this positive reflection. And it jumps up for 2 times the delay of the impedance. Okay, so it jumps up. It looks like here it went from 2.5 to 4.5. Well, lo and behold, that's 2 times the delay of the impedance discontinuity. And you can actually measure the time delay of this transmission line or this impedance discontinuity. Just take that distance right here and divide it by 2. We see a voltage which is 1.2 volts. Now, which of that is reflected? Which of it was there? Well, we know what was there because it's 1 volt. So here's 1 volt. So then the reflected voltage, which is superimposed onto that at this node right here, is 200 millivolts. And that is due solely to the impedance discontinuity between 50 ohms and here. And what's neat is this 50 ohm delay right here. It doesn't matter whether it's 100 picoseconds or 10 nanoseconds. There's no impedance discontinuity until you get to your DUT, and then bing, you have a reflection. It travels back, and you see it, and that's it. So if I use this number, what I can do is I look at my V reflected. It's gamma times V incident. V incident is 1, so it drops out, and we don't even need to really care too much because we just measured V ref directly. But you have to remember that you don't plug in 1.2 for V reflected. The reflected voltage when in this particular waveform is 0.2 because that was 0.2 returned and was superimposed on what was there. So then if I plug this into my values here, my little equation, I've got ZL equals this whole thingamajig. So I plug in 0.2 for V reflected here and here, plug in 50 because my 50 is what I'm in, and I get 75 ohms. If I go back up here and check it, I see 75 ohms. We did it. Okay, let's hear kind of the last thing I'll end with is actually, so your homework is going to be to do this. I'm going to give you 3 of these waveforms, and I want you to figure out what the reflected voltage was, plug it into this equation, and tell me what the load was of the DUT. Okay, so that's going to be your homework. A little more advanced here. This picture right here is a TDR scope. So this is my TDR scope. Actually, it's probably MSU's technically. It's MSU's technically. But I like to call it mine because I bought it with my card or whatever. And anyway, it's expensive. I mean, these things are $50,000. And if you look at it, it looks like an oscilloscope, but it's like a monster oscilloscope. This thing weighs like 80 pounds, and they're better today. I bought this like 10 years ago. But you can see it's an oscilloscope, and it's got the 50 ohm outputs. And what we're doing here is you see these nice thick cables. These are real expensive 50 ohm cables, so that they're exactly 50. They're not 45. They're not plus or minus 10%. They're rock on 50 ohms. And then you come into whatever DUT you're going to do. Look at this DUT right here. This was one of these class projects. This was what you were going to do if we wouldn't have had this pandemic. But you were going to build a printed circuit board and look at kind of some signal integrity issue. So these students made a board that would look at crosstalk. And not just crosstalk, but you could look at crosstalk. But since they put connectors on here to drive the victim, you could also drive the victim with the same polarity or opposite polarity of the aggressor. So you could measure even mode impedance and odd mode impedance. And these TDR scopes, lo and behold, they have two outputs. So you can actually drive differential signals out to this. And there's a little button on the front, and you can turn the polarity. So what we started off with was we connected the oscilloscope main channel to this wire right here. And then I put little 50 ohm termination caps on here. And we measured and we looked at the reflection, and we were able to see the characteristic impedance of this coupled region. The cable coming in was 50 ohms. This trace right here is 50 ohms. You'll notice it's huge. That's because this is a 2-layer 62 mil board. That means this thing right here is about 120 mils wide to get 50 ohms. And then once it gets into here, you see a coupled region. So that 50 ohm drops like crazy. And then after it gets here, it goes back up. If you look at this green wire or line, this is what the TDR measurement looks like. So it comes along, it's perfect 50, it's in the cable, in the fit cable. All of a sudden, boop, 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 all these bumps and wiggles. That is the reflections off of this connector. So the connector has kind of an inductance to begin with, and it has like this big capacitance as it gets onto the board and you get onto this plane. And then it's bouncing all over. And here's the 50 ohm trace right here. So this is the 50 ohm trace right here. Notice that it's not perfect. It's like 48 ohms maybe. That's because you don't get exactly 50 ohms. You try to get as best you can on a printed circuit board, but sometimes you don't. Then look what happens. It gets into this coupled region, and look how the impedance drops down. And then once it gets to this region again, it jumps back up to what I tried to get 50 ohms. Maybe I got like 48, and then it's done. All right. Then you connect another channel of the TDR to this guy, and you start driving in signals. So check out what happens here. The yellow right here, I'm driving into here, and what I did was I measured. In this case, they didn't drive it. Okay, these waveforms are not for driving it. So what they did is they just observed on another channel of an oscilloscope, but they were able to look at the far end and the near end crosstalk. And so they're able to do this and then do that. And that was with nothing being driven. And then it's not shown on here, but then we flicked a button and we were able to measure the even mode impedance because we would drive both of these at the same time. And then you've changed the polarity of this channel right here, the victim, and all of a sudden you're measuring the odd mode impedance, and it's just awesome. Okay, so I just want to highlight this one more time. So your homework for this video is basically you're going to go and plunk in some numbers based on waveforms. So I'm going to give you 3 of these waveforms with different values here. You plunk in the number into here, and then you tell me what the impedance was of the DUT. Okay, that's it, and good luck.